Okay, here are the notes for section 11.2, limits of motion, the area problem. So example 1, an automobile travels at a constant rate of 48 miles per hour for 2 hours, 30 minutes. How far does it go? Well, this is relatively straightforward. Distance is equal to rate times time. So 48 miles per hour times 2.5 hours gives us 120 miles. So, all right, an automobile travels an average. How far does it go? Well, this is actually going to work out to be exactly the same thing. So the average rate of change is, so let's see how to phrase this best. So this 48 miles per hour is delta S over delta T. So if I multiply both sides by, so delta S is equal to delta S over delta T times delta T. So delta S is what I'm solving for. That's 48. This is 2.5. So 120 miles. Same number. So it doesn't matter. So at a constant speed of 48 versus an average speed of 48, you get the same answer. It doesn't actually matter how their speed varied as long as you know their average speed. All right, so limits at infinity. When you write x approaches infinity, f of x with L, meaning that f of x gets arbitrarily close to L as x gets arbitrarily large. Okay. So the connection area, example 3, uses 6 rectangles in the figure below to approximate the area of the region below the graph f of x equals x squared over the interval 0, 3. So we're just going to essentially add up the value of these rectangles. So let's see here. Each rectangle is a half unit wide. And then so I can find the area by figuring out how tall they are. So let's see here. And it looks like we touch on the right edge. So this point here is at 3, 9. This point here is at 2.5, that's going to be 6 1/4. 6.25. This point here is at 2, 4. This is at 1.5, 2.25. This is at 1, 1. This is at 0.5, what's it going to be? 0.25. So the first area, the first rectangle, is 0.25 by 0.5. All of them are so it's height by width. So the second one is 1 unit tall by 0.5. So that takes care of that one and that one. Then we got 2 1/4 by 0.5. Then we got 4 by 0.5. Then we got 6 1/4 by 0.5. And we got 9 by 0.5. So these are the areas of the individual rectangles. So this one would be 0.125. This is 0.5. Oh, this is, so that's 4.5. This is 3.125. This is 2. So this is 1.125. And if I total them all up, that'll give me the total area. So, oops, menu, 0.125 plus 0.5 plus 1.125 plus 2 plus 3.125 plus 4.5. So the total area of those rectangles is 11.375. So estimating the area. All right, so we've got here is referred to as the definite integral. Let f be a function defined on some interval a to b, and let the sum from 1 to n of f of xi be delta x, be defined above. The definite integral of f over ab, denoted by integral ab of f of x, is given by this, provided a limit exists. You say that f is integrable on a to b. So what's happening is we're making an infinite number of rectangles. So in this shape, we're making the rectangle smaller and smaller and smaller, and as that happens, they match more and more closely to the curve. So if we add up the areas of those very, very small rectangles, we'll get the total area underneath the curve. So this is just an approximation. So that's what's happening with this formula. Okay, so let's look at this. So compute, find from 1 to 5 of 2x. So let's look at our graph first. So 2x for 1, 2, 3, 4, 5. So essentially you got a straight line like this. So at 1 here, you've got the point 1, comma 2. Way up here, you got the point 5, comma 10. So we're looking at that shape like that, which is actually a trapezoid tipped on its side. If you think about it, it's actually this shape. So the area of a trapezoid is, let's see here, the height of the trapezoid, b1 plus b2 all over 2. The average of the bases, where this is b1, this is b2, and there's h. Now be careful because you're tilted on its side. So the height is actually this distance here. It's 4 units tall. b1 is this distance, or 2. This is your other one, 10 over 2. So this becomes 4, 12 over 2, 4 times 6. So the area under that curve is 24. So we just approximated the area with the geometric shape that it is. All right, suppose a ball rolls downhill, says the velocity after t seconds is always 2t. How far does it fall during the first 3 seconds? So a similar thing, we got the same graph, except we have a triangle. So here we got the point 0, 0. Here we got the point 3, comma 6. So this is a lovely triangle. So area underneath that is 1/2 the base, which is 3 units wide, times the height, which is 6 units tall. So that is 9. So it falls 9 feet. So there you go. If you have the velocity graph, distance is the area underneath it. Okay, because this is essentially you're multiplying the velocities, the y values, by the time the x values, and that gives you distance, and you do that for every single thing. So it comes out to be 9. That is the end of the section.